Hello. We are going to talk here. Well, I'm going to talk, I guess. You can talk if you want, but I won't be able to hear you. Conservation of mechanical energy. That's a mouthful of physics words. Conservation of mechanical energy. Now, if you were going to pick someone's brain for physics information, somebody who is not in a physics class, maybe somebody who'd never even taken physics before, ever, there's a few things you might find in their brain as you were picking it, looking for physics stuff. You might find things like, I don't know, so here's, I don't know how important it is. Actually, I do. It's very not important for you to include this in your notes, but physics sort of sound bites. You think the sound bites, the bites is spelled like that? I don't know. Sound bites, maybe that's with an I. Here's some. There's the whole, like, Newton's third law. Every action has an equal and opposite reaction, which is a really terrible way of stating the third law, I think. I think people have heard about E equals mc squared. They probably don't know what it means. Let's see, what else is out there? Some statement of Newton's first law, a body at rest will stay at rest, blah, blah, blah. That's usually not stated that well either, because it says unless acted upon by a force, but really it should be like an unbalanced force, because there could be lots of forces acting on something, and if those forces are balanced, then the motion of that object is not going to change. It'll keep doing what it's doing. There's those ones, and then here's another one. And this one kind of, it's, I guess, at the boundary of physics and chemistry and other things. Of course, humans, we're the ones who come in and say, oh, here's like the whole world of things that we observe, and then we draw these lines between them and say, let's call these ideas physics, and let's call these ideas chemistry, and let's call these ideas over here biology. And of course, we have to come up with, when smart young people such as yourselves go off to universities and study things, sometimes you guys study things that are like biochemistry or physical chemistry, or, anyway, that just points to the fact that these lines, we make these up, humans, and, the universe is out there doing what it does, not really giving a crap about us. Somewhere in the boundary here, I guess, there's this soundbite. Energy can neither be created nor destroyed. Can you do it? So, what's up with that? Well, energy can't be created or destroyed, but it sure can move around a lot. And right now in physics, what's the deal with this? What does this qualifier mean? What is mechanical energy? So in general, you could, if you just wanted to talk about conservation of energy, just conservation of energy, never mind that mechanical part, sure, energy in the whole universe is conserved. It can't be created or destroyed. It can move around. Some energy that was stored as, like, I guess you could say chemical or even like atomic energy in some kind of gas or whatever is converted into other kinds of energy when it's combusted in a star, for example, and many, many, many examples of that. So the first thing that we need to, of course, that's a little bit beyond, that's not what we're interested in physics. We're interested in kind of like a human scale energy transfer, like objects that we observe. What means this? mechanical energy is the sum total of all of the potential energy and kinetic energy. That's what we're talking about. So if you're looking at this and thinking, well, what's missing from this list? What are the other things that are not included in this mechanical energy? There's no chemical energy. There's no thermal energy. There are not other things like that. This is the mechanical energy. It's really the kinds of energy, the energy that we think about in the kinds of situations that we tend to study in an introductory physics course. Of course, this is AP Physics C Mechanics, so no surprise there that mechanical energy is of particular interest to us. Also notice here that there's no dissipated energy. I guess I said thermal energy before, but mechanical energy does not include like work done by friction, for example, energy that sort of leaks out of a system in the form of thermal energy. That is not part of this. Okay, so what about potential energy? Well, now that you've done a little bit of lab work, potential energy, we are going to be interested precisely in two different types that potential energy takes. And then a little bit deeper into this chapter, we're also interested in like when a potential energy function is just defined for us. At the two that we are going to be interested in right off the bat here are spring potential and we're going to represent that with a capital U sub S for spring, and that is equal to, you guessed it, 1/2 kx squared. Now if you're looking at this and saying, hold on a second, Mr. McGrath, you just redefined that's just like work done by a spring. Well, no, not exactly, because the work done by a spring, like the spring has actually transferred that energy. It has actually done work. So we're just kind of recasting that idea. If you're looking at a connection between work and potential energy, absolutely, it is there 100%. But the potential energy we define for, like, if you have a spring and it's compressed some distance x, then there is energy stored inside this spring. It's not, if you released it, then that spring would do work on whatever object it was compressed up against. But right now, there's just energy stored in it. And that's what we were defining here. And that's really a little bit different than what we were doing in Chapter 7. So here's our spring potential. And then the other is gravitational potential. And I know you knew about that. You've talked about that in some physical science course you took or something. And we're going to symbolize that with capital U sub small g. And that is mgh. Now this h, that deserves a little bit of talking about, a little bit of qualification, like height with respect to what? Well, with respect to whatever you want, so long as you are consistent as you work through some kind of situation where you think that energy might be conserved. So what I would recommend for you is that this is the height relative to the lowest point that an object could be at in the situation that you're looking at. So right now, say, like, what would your zero height be for this pen if you're talking about gravitational potential energy? Well, right here would be its zero height, right? I can lift it up a little bit, and then drop it, and the mgh, mass of this pen, times 9.8 newtons per kilogram, or meters per second squared, whichever units you want, and times the height of it, I don't know, maybe 15 centimeters here, it's got that much gravitational potential energy. What happens when I let go? Well, it doesn't have any anymore. Where did it go? As the pen was falling, the gravitational potential energy was turning into kinetic energy. Now, when it hit the paper here, there was what we call a non-conservative force. So the force of the paper, the desk, my little recording stand here, that force, that supporting force there, that normal force, acted on the pen, and that is not a conservative force. So mechanical energy was not conserved anymore. We'll come back to that idea in a second. Got a little bit off track there. We were talking about how much gravitational potential energy the pen has and where the zero height is. So it would make sense to say that this is the zero height. This is where it has no gravitational potential energy. But then you say, what if you move it off to the side and then you drop it on the floor? Well, fine, but I wasn't going to do that here. So if I was going to drop it on the floor, then I would pick the floor as my zero height. And everything is going to work out fine so long as you stick with whatever your decision is. Now, you might be thinking to yourself, okay, I get that, but isn't there any kind of absolute sense of what the gravitational potential energy of something is? And the answer is no, not really. There isn't. It's just the thing that really matters when we're looking at how energy shifts around is the change in gravitational potential energy. So sometimes you see, instead of it being defined in an absolute way like this, we see this instead. Now, of course, if you pick h equals 0 to be the lowest point, then this really just turns into this one turns into this. So it doesn't really matter. For our purposes, I would like you to use this, and I would like you to very sensibly choose whatever your zero height to be the lowest height that the object is going to be at in that particular situation. All right. So mechanical energy is conserved. What does that mean? Conserved means it stays the same. Mechanical energy is conserved if there are no non-conservative forces. Now, if that doesn't seem like a tautology, then I don't know what. So just break this statement down here. Mechanical energy is conserved if there are no non-conservative forces. So if there's nothing to stop it from being conserved, then it's conserved. Basically is what that's saying. So what does this mean? It means if the only forces that are at play are forces that have potential energies associated with them. In other words, what are these conservative forces? If we don't want any of those, conservative forces are forces with associated potential energies. And for us, that means we're talking about the force of gravity. That is a conservative force, right? because it has its associated potential energy, and the force of a spring, because that has its associated potential energy. That's what we're talking about. So if you've got a situation, and you will have lots of them, where the only forces you have are some combination of gravity and springs, you don't have to have both, you could just have one or the other. Of course, I guess this is always hanging around, but it might not be changing the location. Of course, this really comes into play when an object is changing its height. If you have one or both of these in play, then you have a situation where mechanical energy is conserved if there are no other forces. So what are these non-conservative forces? The non-conservative ones are anything else. An applied force, like if you're pushing on something, that's not a conservative force. You could imagine, like, if you push on something and then you stop pushing on it, it's not going to rebound back, unless you're pushing it against a spring, right? Friction is a non-conservative force. All these things that you could imagine either add energy in or take energy out of a system. Those are non-conservative forces because they're changing the total amount of mechanical energy. So these are the ones that do not change the total amount of mechanical energy. It's just it gets stored up in the system. Let's see. I would like you to note what the relationship is between force and potential energy. So for gravitational force, here we would have gravitational force is mg, and to make sure that we understand, since we're talking about changes in height and something moves up, that would be positive, then the direction of that force is down, so I'm going to put a negative sign there to indicate that. And the associated potential energy is mgh, where this is like that, the variable position. And here, for spring force, we'd have negative kx, that's from Hooke's law, right? Spring force is equal to negative kx, and spring potential energy is 1/2 kx squared. So what is the relationship here? Well, mg, this is negative mg, this is a constant, and this is the same constant but times that position variable, and we lost the negative sign. Here, kx turned into 1/2 kx squared, and we lost the negative sign. Well, these things are just the antiderivatives of these. Whoa, calculus. Or, if you like, the derivative of this is this, and add a negative sign. The derivative of this is this, and add a negative sign. And in general, the derivative with respect to position of potential energy as a function of position, of course those variables have to match up, right, is equal to the opposite of force. So that's the calculus relationship between these things, and that's going to be important for us when we think about reading a potential energy curve a little bit later on. Okay, I think that's what you need to know. So just real quickly, how do you use all this information to actually do physics, to like do some problem solving? Well, you find a situation, or you examine a situation, and I'll give you an example here. How about a, let's see, let's do one that's a little bit not too complicated. Let's say we have some kind of like spring launcher thing, like a little spring marble launcher. I have one of those that we would have played with it. It's sad, the things that we can't do here. So let's say we got this little marble launcher thing, and so the marble gets compressed against that spring, and that's up on this table here, and it gets launched, and then it lands somewhere here. And of course we'll think about not what's happening like after it hits the ground, but just when, like, right at the instant when it like sort of arrives at the ground. So energy considerations. What's going on? So let's think about the energy here and the energy here. So it's sort of like initial energy and its final energy state here. One way that I have in the past got students to think about this is by making little sort of pie charts. And you can imagine that if the total, oh, first of all, I guess we should ask, are there any non-conservative forces here? Well, let's see. I definitely have gravity at play because this thing's going to change its height from here to here. And there's a spring. Are there any other forces? Well, after it hits the ground there would be, but we're not going to pay attention to that. What about air resistance? That's a kind of friction. Well, this is a situation where probably we're just going to ignore air resistance because this is going slow enough that it's not going to be that much of a factor. So are there any non-conservative forces? No. Okay, so where should, does the object change height? Yes. Where's the lowest point that it's going to be? Right here. So this is where the h is 0. And this is where h is not 0. So if h is not 0, then I've got some potential gravitational potential energy. So a slice of the pie is devoted to that. And then also it's compressed up against that spring. So there's also some spring potential. And down here, it's at height 0, so there's no more gravitational potential energy. This spring has sprung, so there's no more spring potential energy, but it's moving, so it's got a bunch of kinetic energy. So you could think of it as the spring, the energy stored in the spring, and the energy stored in the Earth marble system, because the marble was separated from it. That energy has become kinetic energy. So great. What do you do with those pie charts? Well, you write an equation. You can say that the spring energy plus the gravitational energy here in this pie must equal the kinetic energy, right? Because energy can't be created or destroyed. Well, more this, I guess. Because there are no non-conservative forces here, the mechanical energy is conserved. So that allows us to write a nice little equation, and then spring potential, that's 1/2 kx squared, and the gravitational potential energy is mgh, where h is however high that is relative to height 0. That's equal to 1/2 mv squared. And then, you know, probably know some of these things, and you can solve for other things. What if you have a situation where there is a non-conservative force and some energy is lost? Then is this whole idea just a bust? No, not at all. So let's say, this will be the last example, I promise. How about this situation where you have a block zooming along here with some initial velocity that is greater than 0. And then this is frictionless. Coefficient of friction is 0. And then it gets to this ramp and it slides up to the top of the ramp, or somewhere up there. And that's the highest that it gets. And the coefficient of friction on this ramp is greater than 0. So there is going to be, as it grinds its way up the ramp there, there's going to be some energy lost. So how do we deal with that? Because we don't have, mechanical energy is not conserved anymore. So can we handle this? Well, yes, we can. So here the height is 0, because this is the lowest point that it's going to be at, that we care about right here. So what's happening here? It's at height 0, so there's no gravitational potential energy. It's got velocity, so there's some kinetic energy. There's no springs in this situation, so it looks like here we would just say it's all kinetic. And then up here at the top, how about now? Well, it's not at height 0 anymore, so it's got some gravitational potential energy. But some energy, because there is a non-conservative force friction here, there's energy lost. And there's different ways that you can symbolize this. I like doing this E dis for dissipated energy. Our book sometimes calls this E thermal, that there's some energy lost to heat. So I'm not going to fuss at you what you call it, but there's something, somehow or other, we have to account for the fact that there was energy lost here. So we could write an equation here, just like we did in this example. This kinetic energy would have to equal the gravitational potential energy plus the dissipated energy. If you're thinking to yourself, wait a minute, wouldn't it be like minus the dissipated energy? No. It's if you think about our accounting scheme here, this is definitely bigger than that. So if we're thinking of this as like the positive amount, like the absolute value of that energy that's lost, then it would definitely be plus that. You could, I'm not, there's other ways that you can do that, but I think this is the way that's the most consistent and least prone to accidentally making some kind of sign error. So we just think about all these energy quantities as being positive, can't have negative energy, asterisk next to that statement, and I think that makes the most sense. So if you know stuff about how high it went, you can figure this out, and you might also say, well, oh, the energy dissipated here was the work done by friction, and you know, like if you know the frictional force, you can figure stuff out, and force times distance, all that. So this leads to a lot of very fruitful problem solving for us, and try some of those problems now.